Okay, so here's the rotor, just showing a still shot of it. And while we're at that, I'm going to ask you all a little question. See if you can answer it. When is the maximum power, voltage and current produced across the coil relative to the magnet's position to the coil? Will that be the peak voltage produced or peak power produced when the magnet is directly under the core, or will it be when the two magnets, or the core is between the two magnets, or will it be slightly off to one side? Who knows how the waveform is produced across the coil relative to the magnet's position to the core? Has anyone actually really had a good close look at that? Anyway, I'm going to pull this one apart. Now, these coils are only stuck together, not even with a lackey band. It's one of the white hair lackeys is all I could find. Both surfaces are relatively clean, so they get a relatively good contact. I'm going to face them down a little bit better, make sure they're exactly perfect, so as we get a good connection. Anyway, that's our rotor, north south, and same underneath with these magnets. There is no magnets in the middle, simply one on top, one on bottom of the rotor, which still essentially gives us one big magnet with a little bit of a gap in the middle, but it'll still be north, south, blah blah blah. Okay, so what we're going to do here is I'm just going to show you a few things. We're going to spin this up to speed, and then what we're going to do is a little drag test on the rotor to see actually how much force is required to show a reflection on our current draw. And for that, I'm simply going to take this nice soft bit of wire here and just rest it on the inside the rotor there. So it's not actually going to be on the outside diameter, it's actually going to be a little in, probably half the distance between the centre and outer edge of the rotor. We're simply going to rest that on there like that and see what happens to our current draw. The next thing we're going to look at the difference between a steel laminated core and a ferrite core. Now these core halves, like I said, are out of a TIG welder. They come out of this U-boot part here, and as you can see they used to sit in there to couple the two coils together. So that's where they came from, and they simply used to sit in there and all go together. I did have 4 of them, but I dropped one, didn't I? Anyway, so what we're going to do once this is spun up to speed, we've done our little drag test on there to see just how sensitive our ampermeter is in relation to the drag on the rotor. We're going to try one single laminate out of a transformer. It's a silicon steel laminate, and we're simply going to put it over here like this to represent that there, and we're going to look at what effect or what drag that places on the rotor. And this laminate is simply out of one of these transformers, a bigger transformer than that, and I've just cut the middle section out so as we have something like this. Once we have checked the steel, we're going to see what our ferrite core does when we place it over there and see if there's any drag from that one. This is going to show you why it's so much better to use ferrite than steel. So what you're going to see with one, you'd have to imagine 15 or 20 of those all stacked together like that, sitting over your rotor. think you're going to get a little surprise as to how much difference there is between the two. Remember, one skinny little laminate compared to this big chunk of ferrite. Alright, so I'll turn the camera off now, get this run up to speed, because it takes about 1.5 minutes, 2 minutes to get up to speed. Like I said, it's a very weak motor, and there's quite a bit of mass on that rotor, so it does take a bit to get going. So we'll be back when she's up and running. Okay, so we've broken out the tripod for this, so it's all nice and steady. I hope you can see the meter clearly. Will fluctuate a very small amount due to power instability around this area, but not very much. So well, first we're going to take out a nice bit of soft wire, and I'm simply going to set it on the rotor like A, and you can see that it is detecting that quite nicely. Like I said, it's only just sitting on there, I'm not pushing on it, and we're actually fairly close to the centre of the shaft. So like I said in the first video, I'm using a very weak motor to detect any changes whatsoever. So the other thing I want to point out is this is a big chunk of ferrite compared to this skinny little laminate, and you'll also see the laminate is wider, so the steel parts of the laminate are going to be a lot further away from the magnets than what our core here is. So one skiddy little laminate out of a transformer, we're simply going to put it in a position like that over the magnets, and we'll see what happens. You can see the amp draw is going up and up. Now the frequency is about 102 Hz, so it's very low. So our steel laminate is putting quite a bit of drag on our rotor. So you can imagine what 15 or 20 of them stacked together would do. Now we're going to take our big chunk of ferrite and we're going to place that over the rotor. As you can see, our current draw is coming down close to where we started before we put any cores whatsoever over it. Push them in a little bit further. $165.2 milliamps. Grab our steel one again. that over, and up she goes. Quite quickly. 166. Push this one as far as I can get it, just before it's hitting the rotor. And as you can see, the current draw is once again coming down. So this big chunk of stuff here places hardly any drag on the rotor whatsoever, while this tiny thin little laminate, one laminate, puts a fair bit of drag on the rotor. Now, like I said, this with this motor on this rotor, or this rotor on this little motor, can detect very small changes. It's extremely clear to see that that one little tiny steel laminate by itself is far worse than this big chunk of ferrite core. And remember, the two bits of the ferrite core are a lot closer to the magnets than that one steel laminate. So I'm sure you can see the difference in distance. Oop. So steel laminate's no good. So there's the difference in distance we would have had. So the steel laminate a lot further away from the magnets than this big chunk of ferrite, but the ferrite causes near bugger all drag, whereas this one little laminate pulls it down very hard. So what I'll do is grab my side cutters. I'll cut the middle out of another one. We'll stick two together, see what happens. Now these still have the glue on them, so they're going to be relatively insulated. So now we've got two together. And up she goes. Quite fast. So steel laminates, even at low frequencies, bloody terrible. Stay away from them and use ferrite cores if you can. Even all those guys building fluxgate generators, and that is a very good example of eddy current losses in steel laminate cores. So there you go, Luke. You might be better off seeing if you can find some big chunks of ferrite. Your system will become more efficient. Terrible, bloody terrible. Alright, so that's going to be it for this video. I'm going to rewire these cores. I'm even going to do this third one as well. And I'm going to put some little test coils on them along the horizontal top leg of the cores, and we can have a look at the magnetic field going through this one, and then what would be the next one. Here I'll put another little coil on the top there, and we can have a look at the difference between the two. see as to why the back coil is receiving a magnetic field change faster than or earlier than the front coil. Alright, thanks for watching, guys. I hope that has shown you just how bad steel laminate cores are and how much loss you're going to have using them. Once again, thanks for watching.